Hi, I'm Amy. I'm from the Seattle Google office. And so you probably know what developer relations does, but essentially we're sort of public-facing engineers that try to help people like you use Google stuff. That's sort of the very high-level view. So, so what I'm going to do in this talk is introduce Spanner, which is newly released, although not new inside of Google, and just kind of give an overview, give a few little demos, one hopefully kind of showing it working at scale, talk a little bit about how it works under the hood, and just kind of have a general goal to get you interested in it. I think it's really, really cool technology, so that's sort of my goal, is to get you thinking that as well, and you know, go and maybe look it up and poke around with it yourself. So who has heard of Spanner? Or, oh, wow, cool. Great, okay. All right, so a little bit of background, a little history story. Back in 2005, I wasn't at Google then myself, by the way. The AdWords part of the company, which is a big moneymaker for Google, was using sharded MySQL cluster for all their AdWords stuff, and apparently they were sharding by customer ID, and every time they did a reshard, it was just hugely laborious and time-consuming. And apparently, I don't know if this is true, I was told that one reshard actually took them 5 years. I don't know if that could possibly be true. And you know, they needed the ACID semantics, and every time they had downtime for some reason, it actually cost them a lot of money. So they decided internally, well, we need something better. So they said, well, we need horizontal scaling. We need to keep the ACID semantics that we already have right now, and but we want to be able to have that globally because we're starting to expand, and ideally, we'd like to not have any downtime, because every time we have that, like even if it's scheduled, it really costs us. So, so they went to work. A lot of very, very smart people, supernaturally smart people, were working on this, and even so, I've heard that, you know, it took them a lot of thinking and several iterations to get this right. So fast forward again, 2012. This was when the OSDI paper on Spanner came out. Has anyone taken a look at that paper? It's really very interesting. Oh, cool. And if you haven't, I would actually suggest you start with the video of the paper talk at the same conference that's also online. I think that's a nice, very accessible, interesting introduction to what Spanner is. And then go take a look at the paper. Okay, so now, fast forward to 2017. So a decision was made at some point. Well, let's externalize Spanner, and so that is what Google did. So it's now a globally distributed database service that anyone can use, and with amazing timing, it just went GA, general availability, yesterday. So this is a well-scheduled talk. So. And just to kind of highlight this point, it's the same Spanner. So unlike some other things Google has released that are, you know, sort of like an externalization of technology that they've used for a while, but you know, build a little differently. This is the same Spanner with just like a layer of cloud platform stuff on top of it, you know, dealing with cloud platform projects and access management and things like that, which is pretty cool. Okay, so what exactly is Cloud Spanner? So it solves kind of a long-standing problem with large-scale databases. So you have either you go with relational databases because you need transactional semantics, and then when you start to get big and you've sort of maxed out how you can vertically scale, then horizontal scaling, can be problematic. And there are all sorts of frameworks that try to help you address that in different ways, but it can get tricky. And then sort of the other side of the coin is you can pick a NoSQL database that makes horizontal scaling a lot easier, but then you lose the transactional semantics. So then you typically end up building that into the app level, so to speak. And so what Spanner does is support both of those together. So it's globally distributed database with strong consistency, ACID semantics, but also scales horizontally and transparently for you, and is highly available. What's out there right now is 4 nines, and soon 5 nines will be available. I'll talk a little bit more about that. And it's fully managed, so you don't need to deal with any replications, backups, security updates, anything like that. And so at this point, I just have to mention what JD said earlier. He said, why would you run on any system that didn't support ACID semantics? And so that's certainly a Spanner's point of view. Okay, so this is mostly a repeat of what I just said. It's just kind of to hammer the point home. It's been used internally in Google and really beat on, for a number of years, and that's the same infrastructure that the externalized service is running on. Okay, and I'm not going to spend too much time on this slide. It just kind of repeats what I just said. Spanner, Spanner makes the case for, all right, we get the best of both worlds here. However, I do need to mention one very important thing. So it uses ANSI SQL 2011, but Spanner does not currently have a DML. So what that means is you can define your tables and indexes. You can make queries. If you want to do mutations, if you want to do transactions, you need to do that programmatically, not through SQL. That will come, but it's not there yet. So obviously that has some implications in, how you might port some other existing system over to Spanner. It's not just going to be a drop-in place if you're, using Oracle right now, for example. Okay. So standard SQL. It in terms of the API, it supports has a REST and gRPC APIs, and also a growing set of client libraries. So right now, Python, Go, Node.js, and Java are supported, and there are some more to come shortly. Ruby, C#, PHP, and there is a probably can't tell. I wrote the JDBC driver part in slightly lighter gray. It's read-only at the moment, but there is a read-only JDBC driver as well. And about the lack of the DML, it turns out that there are a lot of subtleties to supporting that in SQL-based DML for a distributed database like Spanner. So they are working on that, and it will come. Okay, so at a very high level, the way the Spanner architecture looks, so this is from Cloud Spanner point of view, is that you create Spanner instances, and those are currently single region, and soon multi-region will be supported as well. I'll actually show a demo that uses multi-region, just so you believe me, but it's sort of not quite there for the user-facing stuff. So so you pick a region. You can be whatever part of the world. I'll show you a drop down. You can pick from Europe, Asia, or U.S. And then within that region, Spanner is going to take care of everything for you in terms of the replication. So it will, as you define your databases in the instance, it will replicate that data in multiple zones. And so you can sort of get the gist from this picture here. All the databases you've defined are in multiple zones. And then if some update comes in, it'll come into one of the zones, and that data is synchronously replicated to all the other zones. So it's high availability. It uses a custom Paxos algorithm for the replication consensus. And you don't have to think about any of that or worry about any of that yourself. Okay, so dropping down one more level, so now this gets to the horizontal scaling out part. So when you define an instance, a Spanner instance, you can specify how many so-called nodes you want to use for that instance. And you can change that. It's not like a one-time choice. So the nodes are like compute power, and that is what gives you your QPS, your throughput. And so if you suddenly get hit with a burst of popularity, maybe you made some app and it's on Hacker News or whatever, you can go in and bump up the number of nodes that you're using for your instance, and that'll increase your throughput. So the these guys are sort of like roughly representing the nodes. So we've set this up. We set up this Spanner instance to have 3 nodes. So the important thing to realize is that Spanner is taking care of the zone replication, right? So that means you get that much compute power across all your zones. So you're not having to specify like number of nodes and multiplying by how much replication you want. You just think of it sort of in compute power units, and it scales out. All right, so let's talk a little bit about schema design, because with this kind of database, there are some considerations to keep in mind. So this would be sort of like a typical relational data design. The example is you have singers and they have albums, and you probably have a join key, probably have a foreign key. So with Spanner, there are no foreign keys. Instead, what you do is something that's called interleaving. You interleave your table definitions, and this is essentially a design constraint imposed to let Spanner get more leverage in terms of what it wants to do to distribute its data. So what we would do in this case is we would define interleaved singer and album information. And what's being suggested here is that the primary key for the albums is composed of the primary key for the singer and then the album ID. And so that's how that interleaving works. Here's a more concrete example. So you decide that you want to interleave singers and albums. You define the album primary key to be a composite of the singer ID and the album ID, and you interleave it in singers. That way you can, that supports cascading deletes like a foreign key would. And also, it says, I want these, I'll go into this in a little more detail a bit later, but basically it says this data is going to be physically co-located. Say you know that you're going to do a lot of joins on this data. This locates it together, so those joins are very efficient. Okay. And then as your database grows, here's where the horizontal scaling comes in. Spanner will divide it into so-called splits. And so I'll show you a picture in a minute. But something to keep in mind is that in this split, Spanner rows are lexicographically ordered by primary key. So that means that close rows lexicographically are going to be stored physically close as well. So that can have both advantages and disadvantages. And then Spanner will only draw split boundaries between rows that are at the root of a hierarchy in the sense of the interleaving that I just showed you. Okay, so here's a picture. What this is showing is showing an instance that has been set up to use 5 nodes. So, and it's doing a split into 10 pieces. So these are these verticals are the 5 nodes. And so you can see that each zone has all the data, all the pieces of the split, of course, right? Because the data is fully replicated between the zones. And but the different zones might not have the splits kind of spread out the same way across the different nodes. And I won't really say much about this, but this is related to it uses some heuristics to decide how to do those splits and where to place them, depending on the usage that it's getting. And so for a given split, there is going to be one leader in the Paxos consensus algorithm sense. And so Spanner actually uses very interesting technology called TrueTime, which I will talk about in a little bit, to do that leader election. Okay, and one more cool thing to mention here is that Spanner allows schema changes with no downtime. All right. So I'm going to try to do a super quick demo. I won't spend too much time on this because hopefully it will all be like kind of as you would expect it to be, which meaning working properly. But here's how you would set up an instance and add nodes to it. Okay, I'm not going to actually go through the process of creating the instance, but I'm going to start to do it. Okay. So create a new instance, select configuration. Again, right now, Spanner only supports single region. Soon it will support multi-region configurations. So I probably would select US. Here's where I am. And I'd decide how many nodes I wanted. And I'll show you in a little bit. Spanner gives you some help in deciding, are you using too many nodes? Do you have too few? And nodes cost 90 cents per hour. So there's no, in case you're wondering, there's no free tier for Spanner. There's, if you sign up for Google Cloud Platform Project, you can get free credits, but there's no free tier for Spanner like there is for some of the other Cloud Platform products. Okay, so if you pop into an instance, you can see a set of databases. And here's one, for example. I will, I'll show you what the monitoring looks like. This is monitoring CPU usage with respect to how many nodes you have defined, for example. Here are a whole bunch of databases. We have our node setting set way too high. So I can go back into the instance and modify that. I would click edit, and I'd ratchet down the number of nodes, and that takes effect almost immediately. And I can pop into one of the databases and see the table, show the equivalent DDL for the tables. And I can do live queries. I'll show you that in just a little bit later. And by clicking this query button, and just generally do a lot of stuff in the UI. Okay, I'll show, and none of that was very high scale. The high scale stuff is yet to come. It's actually piggybacking off a Google I/O demo, so hopefully it's all going as planned. All right, and one more thing to mention here is that we've got these client libraries, and they're all out on GitHub with more to come. And the way to find them is just to, there's sort of a pattern. Go to the Google Cloud Platform org on GitHub, and then look for whatever programming language name, like Python, Node.js, doc samples, and you'll find them in there. Okay. So before I show the hopefully impressive large-scale demo, let me talk just a little bit more about schema design and why it's so important for Spanner. So here's a slightly more complex version of that same example. Now we've got not only albums, but songs on the albums. And so we're interleaving them again. And so the primary keys of the subtables then are prefixed by the primary key of the parent table, like you saw before. And there's another example. Okay, so one thing to be aware of is that Spanner allows creating secondary indexes. And you'll see in just a little bit why that can be useful. And so indexes essentially are just represented as other tables in Spanner. And so you can specify also that they are interleaved. And so that again can, if you do that, that says I'm going to use this index a lot, in conjunction with these tables, and I want you to try to keep it in the same physical location to improve performance. Okay, but you have to pay attention to how you do this, and you don't want to just be like doing blanket interleaving of everything. So here are some things that can go wrong, or things to pay attention to, I should say. So, so you remember that I said that Spanner stores its data lexicographically ordered. And so suppose you have a primary key that is a timestamp, or maybe it's just, like student number or something, and you're adding students and incrementing the student number. That is going to create a very bad hotspot in terms of the tablet, the split accesses, that will really slow things down. Won't break anything, but will really slow things down. So you sort of want to try to avoid hotspots at all costs. They're a big culprit in why things aren't behaving like you would like them to. So some of the ways to address this are to do little tricks like maybe adding a sharding prefix to your IDs, or maybe doing a bit reversal, like get the timestamp, then reverse it, store that, and then actually timestamp is probably not a good example. Maybe student ID is a better example. But some cases where you can reverse whatever it is you're storing as the primary key to reduce the sequential aspect of it. So if you go back to this diagram, you can see that when things are split, they're not necessarily going to be essentially on the same server, and really the more nodes that you add, which adds compute power, the more Spanner is going to scale out horizontally if it thinks it needs to. So this is something that you need to pay close attention to. Split where you can, where it makes sense. Watch out for your hotspots. And then if you have things that need to live together, give Spanner the cues to tell it how to do that by interleaving. Okay. All right. And let me just talk briefly about query optimization as well. Spanner does not try to figure out too much about the query plan. It does some query planning, but it often needs hints from you about how to make the query work better. And so here's one example where we're creating a secondary index. So we're indexing on our primary key is singer ID. Here we're creating a secondary index, singer by last name, and that will improve things if we decide to query on singer last name. But if we realize that we're always looking for first name whenever we query on last name, then we can do this additional little storing clause here, which says when you build the index, include the first name information as well. Remember indexes are really sort of just additional tables in Spanner. And so that makes things, at the cost of a little more storage, that makes things a lot more efficient when you actually query. Kind of the same for like descending. If you're getting results that timing results that seem slower than you expect, you might need to add secondary indexes for sort order. And then finally, there are a number of different kinds of join directives. This is just one that you can tell Spanner to force it to use a secondary index. It's not very aggressive about guessing which secondary indexes it uses. I think it only picks one if everything in the index is part of this select, if I remember correctly. So oftentimes you'll want to tell it, oh, use this secondary index. And I'll have an example query that shows dramatic results from doing that. Okay. And just a pointer to the documentation. If you're interested in this stuff, there's like a whole best practices section in the Spanner documentation that goes into this in more detail. Okay, so now I'm going to attempt the hopefully running larger scale demo. So this is like kind of a ticket sales app. It's sort of Ticketmaster-like. I didn't want to write Ticketmaster on my slides in case Ticketmaster would then sue me, but that's kind of the idea. So it's the database itself is very large scale. I think it's about 16 terabytes or something like that. And hopefully at the moment, it's being constantly hit by a bunch of, it has a client front end that's written in Go, and it's constantly being hit by little purchase bots that are written in Python, actually. All of those little processes are running on several large Kubernetes clusters, by the way. So Kubernetes is playing a role in this demo. Okay. So not only is the database large, but it's active right now, or so I hope. Okay. Semi-active. All right. So I just switched to a separate project. This is a database that has 16.8 terabytes and whole bunch of different tables that relate to this Ticketmaster domain, and again, it's being actively hit at the moment. This is a front-end app that kind of gives the gist of this. So these are real numbers. This is Google I/O is just starting today, and this is being spun up for a Google I/O demo as well. So yeah, I'll show you in a second the multi-region setup. This is a multi-region Spanner instance. So there are servers all over the world, and this is just showing like how hard our bots are hitting it, and what the tickets sold per minute value is, and how many tickets have been sold in total since it got fired up, which was probably this morning at some point, and then some latency information. So if we go to the monitor here, we can see that given how hard it's working, Spanner actually thinks we have enough nodes at the moment. I think we have 50 nodes running at the moment. If we look over the past couple days, you can see there was a point, I think, where one of my coworkers was loading more data where it actually didn't think it had quite enough nodes. And he could have gone in and boosted that count, and that would have taken effect very quickly. So again, adding nodes essentially gives you transparent horizontal scaling out. And then more monitoring information that I, for lack of time, won't spend too much time on. Okay. And actually, I think I'm going to skip, in interest of time, I think I'm going to skip the database query. I was going to show a query in this interface, and then show how it was kind of sluggish and was doing an unnecessary table scan, and then how if you add a force index to make it use a secondary index, it no longer needs to do that table scan. It scans less data, and everything is much, much happier. All right. That's a squint your eyes and look at the schema for this. And this is just a snapshot I took yesterday where it was really kind of working hard to kind of show that, yeah, it tracks, this is CPU usage, yeah, it tracks what you're using and essentially gives you a recommendation if you need to add more nodes, which you can do. It likes to see about 75% utilization. Okay. This is the query that I would have done. All right. But, and I'll make these slides available, of course. So I wanted to take the remaining time to do just a little bit of a deeper dive under the hood, because I feel like this is super interesting. What I showed so far was sort of from a user point of view of, oh, this is a great managed service. There's almost no knobs you need to tweak. It's really easy to use. I want to say just a little bit about what it's doing under the hood as well. So first of all, this is kind of a red herring. There seems to be kind of a common conception that since Spanner makes the claim that it's strongly consistent, right? It has ACID semantics, and it's highly available, that it somehow has magically figured out a workaround for the CAP theorem. And this is not true. And so the CAP theorem says you can't have consistency, availability, and no sensitivity to partitions all at once. You have to pick two of those. So even Eric Brewer himself, Mr. CAP Theorem, it doesn't like that. Suggests that people not look at Spanner through the lens of that. It's kind of a red herring. So it is consistent and it is highly available. And really, what is going on is that Google's networking is really good, and so technically it's a CP system. It always chooses consistency over availability in the face of a partition. But you can sort of think of it in effect as kind of a CA system, given that Google's networking, and all of the work that has gone into making that robust makes the downtime very, very low, especially with multi-region instance configuration. Oh, I forgot to show you that. That big demo was using a multi-region instance configuration. Okay, so that's kind of a red herring, but it comes up a lot. So And that high availability has nothing to do with TrueTime, really. It's mostly just the network, although TrueTime facilitates some things. But let's talk about what TrueTime is and what it does enable. So it's part of Spanner, and you can think of it as sort of a global synchronized clock with bounded non-zero error. And so what that means is that it returns a time interval that is guaranteed to contain the actual time globally. So it essentially gives an error bound. It returns a time and an error bound. And there's a lot of work that goes into making that possible. And some of it is discussed in that Spanner paper. So given that guarantee, then if two intervals do not overlap, then we know that those two calls were definitely ordered in real time. And every transaction has a timestamp. So if the intervals don't overlap, then you know that was the real order that the things happen. And of course, if the intervals do overlap, then you do not know either way. So if you with something like TrueTime, if you can make that guarantee, then you can do some cool things. So Spanner has an external consistency invariant that says basically if transaction 2 starts to commit after transaction 1 finishes committing, then we know that the timestamp for transaction 2 is always going to be greater than the timestamp for transaction 1. And so if you have that external consistency guarantee, then that gives you the ability to basically do snapshot reads without any locking. It gives you a lot of power. And so that invariant is enabled by TrueTime. So that's how it's the use of TrueTime that allows Spanner to support that external consistency invariant. Okay, and so as part of that, to make sure everything holds together, then there are certain times where, like during the Paxos consensus back and forth, where the leader may need to do a commit wait so that it is sure that the commit time is actually in the past, given the error bounds. And but in reality, that's not really like a wait of the server just sitting there twiddling its thumbs because it's doing other stuff in parallel. So it's not a very onerous wait. But there's this concept of a commit wait that you do so that you are guaranteed to have this external consistency feature. Okay, so that is really cool. Again, that lets that enables globally transactionally consistent reads across all of Spanner at a given timestamp, both the current time for some value of that, but also times in the past, because Spanner does versioning. So you can say, all right, give me a globally consistent snapshot of what the database looked like 15 minutes ago. And that is super useful for many things. So something that's really interesting about that is that if you have these TrueTime guarantees, then there's nothing that restricts that to being useful just for Spanner, right? and so that's what's really interesting about this. It lets you do that kind of reasoning across multiple systems, across different systems that aren't Spanner. And so this opens up a lot of possibilities. And so I can't speak to the details of this yet, but Google is actually working on making TrueTime available as a separate service. And that's going to be useful to a lot of people. Like, for example, you can imagine that, CockroachDB might find that useful, for example. so that'll be really cool. So keep your eyes open for that. Okay. So in the few minutes I have left, I probably have 1 minute left, I just wanted to sort of pop back up to where I started and just say a little bit about like when you might want to use Spanner or when you might want to look into using it. So it's not, despite how well it works at scale, it's not just for the cases where you already have like 2 terabytes of data or whatever. I think it's really for any case maybe like where you have like say around 10 gigs of data or something like that. You have a fairly substantial data set, but it's not huge. And you think it might grow, and you know that you need the transactional semantics, then Spanner should be very performant. So there's nothing that says oh I have to use it only if I have a huge database. So and if you think you might need it in future, then it might be something good to look into. And so we're seeing people start to use Spanner for basically sort of like variance on that. Scaling out, they're starting to need higher throughput than they can support currently. They're needing to go global, and they sort of don't want to deal with the hassle of that. And one kind of interesting case is that we're seeing some people essentially use Spanner to do database consolidation, like dumping data from multiple sources into Spanner. Okay, and I just wanted to make one last pointer to interesting reading. In the Spanner documentation, there's actually a white paper section at the end. Look like in the left-hand nav bar once you go to the Spanner documentation. It's more detailed than sort of like the usual just documentation. Some of it's really interesting reading. So I would so if you want to learn more, I'd go to this white papers. I would look at the OSTI paper. Oh, and I wanted to also point you to Eric Brewer's white paper on basically on TrueTime, Spanner, the CAP Theorem, and TrueTime, I think that it's called, which is this right here. Okay. Thanks very much.